So now let's talk generally about our surface and our volume integrals. So for our surface integral, I've drawn sort of this amoebus surface with this black line, and we have some vector field A which is going through it. And so what I've tried to represent with these dashed portions here is we have our A which is coming below our surface, and then the dashed portion, it's actually below our surface, so we can't see it directly, and then it comes through our surface and now it's above the surface. And so with this, we can do a surface integral, and what our surface integral represents is the flux of A through surface S. So flux of A through our surface S. And so we can define this integral by defining some differential surface area on the surface. So we could say, for instance, here we have some differential surface area. So this is some ds. And of course, when we define that, we're going to need some unit normal vector. So it's kind of hard to see. Let me actually take out these lines I drew here in the middle. So let's take out these guys. So we have some unit normal vector, which is normal to that there. So we have unit normal. And we're also going to have some theta angle that's relevant between here, we're going to see in our equations. Okay, so what we would do then is we could say that our flux of A through S, we're going to use the variable psi, is equal to the integral across the surface of A dot, that unit normal vector, times ds. Now, as we saw before, in general, our ds is equal to ds times un. So we could also write this as an integral over S of A dot ds, where we're using a differential normal surface area like we saw in a previous video. And we could also write this as an integral over the surface area of the magnitude of A times the cosine of theta ds. So we have a few different options in terms of how we represent that. And similar to with our line integral, we talked about we could have a closed path or sort of an open path, a line segment. Same thing here in this figure, I've shown a sort of an open surface that doesn't enclose a volume, but if we have a closed surface, our terminology changes a little bit. So if we have a closed surface, what we have then is our flux is equal to the integral over S, and we put a little circle on our integral sign again to indicate it's a closed surface, and that's still going to be A dot ds, however, and we would say that this then represents our net outward flux. So net outward flux of A from surface S. And so sort of a simple case, if we go back to those figures we were talking about with our coordinate systems, we could say maybe we have some spherical surface S, and we're talking about some field that's emanating from that or going through that, then we would have a net outward flux A from S. So that's our surface integral. Finally, our volume integral is relatively simple. So our volume integral, remember, because our differential volume was not a vector quantity, our volume integral is just going to be S sub v, so integral over the volume of rho v dv. So simple as that. And so it's a little harder to go into more details into that because the exact meaning of what this integral is going to depend on our physical problem. So in most cases, what we're going to see is that this rho v is going to represent a charge density, but it can also represent other things. So the physical meaning of what is going on here is going to depend on what our rho v represents, as well in the cases of our surface and line integrals, it's going to depend on what our A represents. So maybe it's an electric field, maybe it's a magnetic field. So depending on what it represents, we're going to have different physical meanings of these integrals.